You are exactly halfway across an oceanic airway in a twin jet when your left engine fails. You must divert immediately. Because the geographic distance to departure and destination are identical, you face a hard mathematical choice: turn back or push forward. To answer that, we calculate the critical point, the fastest path to a runway, measured purely in time. But time is only half the equation. The point of no return is your physical limit based strictly on fuel. Cross this boundary, and returning is impossible. If you drift off course during this emergency, you will need the 1 in 60 rule. This calculation gives you the exact heading correction required to get your aircraft back onto the safe track. Passing the DGCA air navigation exam requires executing these 3 frameworks flawlessly. Confuse a time limit with a fuel limit under pressure, and you fail. This is the formula for the critical point. To find the geographic distance to this point, you only need 3 variables: the total route distance, your ground speed outbound, and your ground speed homebound. Let's test a 2050 nautical mile track. If an engine fails, your outbound ground speed drops to 370 knots, and your homebound ground speed becomes 335 knots. Plug those numbers in, and the math places the critical point exactly 974 nautical miles from your departure. Here is where the DGCA examiners lay their trap. They will ask for the time it takes to reach that critical point. Do not use your reduced engine out speed. You divide the distance by your normal all-engine ground speed, because both engines are running perfectly fine until the exact moment you reach the failure point. The critical point requires you to calculate distance based on a failure that might happen, but calculate time based on the healthy aircraft you are currently flying. Now look at the point of no return. Before you can determine how far you can fly, you have to calculate your safe endurance. This calculation contains a strict fixed reserve trap. If you have 390 liters of total fuel and an 81-liter mandatory reserve, you must subtract that 81 liters before you divide by your fuel flow. If you skip the subtraction step, your math will tell you that you can fly further than your legal fuel allows. This fuel boundary is highly sensitive to the environment. The maximum possible distance to your point of no return only exists in completely still air. Any wind at all, whether a headwind or a tailwind, increases the total fuel cost of a round trip, actively shrinking your maximum safe radius. Contrast this with the critical point. When a wind shift occurs, the critical point behaves predictably. It always shifts geographically straight into the new headwind. Wind shifts will slide your fastest path to safety up and down your route line, but if you fail to subtract your mandatory fuel reserves, you guarantee you will run dry before reaching it. When your navigation breaks down, you rely on the 1 in 60 rule. This requires 2 angles: the track error, which measures how far you drifted off course, and the closing angle, which dictates how sharply you need to cut back to hit your target. Try this scenario. You are 120 nautical miles into your flight. You realize you are 8 miles to the left of your planned track, with 60 miles left to fly. Calculate your total correction angle. Your math should give you 4 degrees of track error and 8 degrees of closing angle, totaling 12 degrees. But here is the directional trap. Because you drifted left, you must apply that 12-degree correction to the right. Apply it to the left, and you double your error. Generating the right number is useless if you steer it the wrong way. Track interception demands absolute spatial awareness when things go wrong. Let's lock this down. The critical point is strictly about time. It always shifts into the wind, and you must use your normal, healthy airspeed to calculate the time it takes to reach it. The point of no return is strictly about fuel. Any wind shrinks it, and you must subtract your mandatory fixed reserves before you calculate your endurance. For track corrections, the 1 in 60 rule requires you to add your track error to your closing angle, and always turn opposite to your drift. These 3 calculations make up a massive percentage of the DGCA exam. Head over to clouddeck.in to run practice scenarios with shifting winds and complex variables. Get these dialed in, and you're ready to tackle radio navigation.